Hello, welcome to Lecture 9, Rotational Dynamics. In this lecture, we're going to look at the concepts of momentum and energy in a new frame of reference. We're also going to work with stating Newton's laws of motions and how they apply to these rotational frames of reference we're using. And as always, we'll need to make sure that we explain and use the correct physics terminology and try and connect those terms and our calculations back to lab practices. A brief outline of this lecture is that we're going to take a look at forces in rotational motion, which we will call torques. So we need to analyze the behavior of objects that experience those torques, which is again a force in a rotational motion. And finally, we need to analyze the concepts of rotational motion and see which ones of them are subject to conservation laws. There'll be some other information that we look at as well. To understand forces in rotation, the key concept is that we need to consider forces that are applied in a manner that will cause rotation. If we consider a circular path of motion that has an axis of rotation and a known radius length, a force applied at the edge of that radius will induce an angular acceleration and hence an angular velocity in the relative direction that the force is applied. Forces applied in a way that induces this rotational motion have a special name, and we refer to them as torques. A torque is a vector quantity, so it has a magnitude and a direction. It works in rotational frame of reference, so we need to consider a sign convention. If the motion induced by a torque is counterclockwise, we will continue with the convention that this is the positive direction and therefore positive torque. If the torque induces motion that is clockwise, then it is a negative torque. We're about to look at the calculations of torque, and this will make more sense at that time, but the units for torque are newtons multiplied by meters. Now we have to look at calculating a torque. Fundamentally, torque is a cross product of force and radius. This is a special way of multiplying vectors. It would look like this. The torque, represented by the Greek letter tau, and it is a vector quantity, would be calculated by taking r, the radius vector of the rotational motion, and cross-producting it with the force vector, which is the applied force. We can actually represent this with a special product simplification here. And to do that, we consider the magnitude of the torque is equal to the magnitude of the radius multiplied by the magnitude of the force applied, and then we calculate that with the sine of the angle between those two vectors. There are two conventions that dictate the way we think about this angle theta. It represents the angle between the two vectors. The first convention is the tangential component convention. For this convention, you measure theta very similarly to the way we've measured theta all the way along, except for this time you start from the extended radius vector and measure counterclockwise all the way back to the force applied. This means that when you calculate F, the force applied, times the sine of that angle theta, you are getting the component of force that is perpendicular to the radius vector. Hence the term, the tangential component, and this is the tangential component of the force applied. The other convention is the lever arm component. This is the one that your textbook describes. The angle in the lever arm component is the smaller of the two angles between the radius and the force applied. Here I'm representing it with the Greek symbol phi. Now, if you were to calculate the sine of phi and multiply that by the radius component, then that would give you the amount of the radius that is perpendicular to the force applied. No matter which of these two conventions you choose, the resulting torque calculation, or the magnitude of the torque, will be equal. Okay, let's clear our screen and bring back our torque equation. And we're going to look at some examples and calculate several different combinations of radius vectors and applied forces. For this example, we're going to take a radius of 31 centimeters, and let's say that's applying to a wrench that's trying to turn a nut. Now, if at the end of that radius, we apply a force of 65 newtons perfectly perpendicular to the wrench, let's calculate the amount of torque. So if we take the torque is equal to our force applied and our radius and the sine of the angle between them, and if we're perpendicular, that means we have a 90-degree angle, and we plug that into our calculator, we'll see that we get a torque of 20.15 Newton meters. Considering significant digits, this is approximately 20 Newton meters. Let's change our situation slightly. Let's look at a force applied in the opposite direction. So we'll keep the same radius, but now we'll have 65 newtons pointing down. In this case, our angle between the two, using the tangential component convention, will have an angle of 270 degrees. When we complete the calculation this time of 65 newtons multiplied by 0.31 meters, our radius, and the sine of 270, we get negative 20.15 Newton meters, which is approximately negative 20 Newton meters. So we see that if we use our original convention for angles, our sines and our sine convention also gets followed. What happens if we keep the force applying straight down, but we adjust the radius over by one set of sides on our nut? So the difference between any two consecutive sides on a hexagon is 60 degrees, which means if we look at our angles a little bit, we can see that the radius points down and to the right, and that if we measure all the way around, that we would have an angle of 330 degrees between the extended radius and our force applied directly down. If we calculate our torque this time, which is 65 newtons multiplied by 0.31 meters times the sine of 330 degrees, we see that we get negative 2.66 and a whole bunch more information, which is approximately negative 2.7 Newton meters. So we notice as our force applied differs from perpendicular to our radius, we decrease the amount of torque we can generate. So as we move down, if we don't adjust our force direction, our torque decreases. We mentioned earlier that a net torque will induce rotational motion. Now, how much rotation depends on characteristics of the objects and its resistance to rotational motion. We calculate this using the equation, the sum of all torques, which is your net torque, will be equal to I, where I represents the moment of inertia multiplied by alpha, and alpha represents the angular acceleration. This should look familiar. This is actually Newton's second law. Remember, force is equal to mass times acceleration, but written with rotational motion components. We need to think about how we calculate the moment of inertia. When a system of particles rotates about a fixed axis, each particle contributes to the object's moment of inertia, its resistance to rotational motion, based on the amount of mass for the particle and its distribution from the axis. So we have an equation for calculating this. Remember, I is the moment of inertia, and it's calculated using the sum of all the masses multiplied by their distance from the axis of rotation squared. A common example is when you have two or more particles separated by a distance. So let's look at a situation where we have a blue mass of 2.3 kilograms that is 1.1 meters from the axis, and a red mass that is 1.2 kilograms that is 1.3 meters from the axis. If we take our formula, I is equal to the sum of mass times radius squared, then we would have 2.3 kilograms times 1.1 meters squared plus 1.2 kilograms times 1.3 meters squared. Calculating all this, we would get 4.811. And notice that our units are kilograms meters squared. Considering significant digits, this would be approximately 4.8 kilograms meters squared. What are the consequences of a moment of inertia? Well, if we think of Newton's second law, we would see that for a greater moment of inertia, our angular acceleration would be smaller for the same level of net torque. And that's what we said earlier. Moment of inertia measures an object's resistance to rotational acceleration. Now, when the number of particles becomes nearly infinite, like when you have a solid body, we have several approximation calculations that we can do to still calculate the moment of inertia. These are called the moment of inertia for rigid body formulas. The first rigid body is a thin rod, and when it says that the axis is at the end of the rod, it means a rod that levers up and down like this, and it rotates at a point at the end of the rod. This would be different than a thin rod whose axis is in the middle, as a thin rod with an axis through the middle spins about that axis like a propeller. We can also have two-dimensional objects instead of just thin rods. We often call these slabs or planks. If the axis is through the center of the slab, then it will rotate flatly around that axis, kind of like spinning a pizza box on your hand. Or if the slab has an axis that is at its edge, it'll swing around that axis, and you can think of this like a door. And one of the final ways that we can think of a slab rotating about an axis is when the axis is parallel to one of its edges, but through the center. This is an odd example, and I haven't quite thought of a real-world explanation that mimics this one. If you can describe any object as one of these shapes, the moment of inertia for any object that fits these descriptions, you can use the formula below it, which takes the mass times the length of the object squared and multiplies it by some approximated fraction. Note that you may be required to break complex objects into multiple parts and combine these moment of inertia equations. Once a particle experiences a net torque and a rotational motion is induced, we need to consider the angular equivalent of momentum. We simply call it angular momentum. For this, we need to consider a circular path of motion that has a fixed radius in which a mass travels at a given velocity. With this information, then we can calculate angular momentum, L, as the mass multiplied by the velocity multiplied by the radius. But this equation wouldn't apply to the situation as drawn, as it's for counterclockwise motion. In the case drawn, we would calculate the angular momentum as negative of the mass multiplied by the velocity multiplied by the radius of the path of motion, as it is clockwise motion. Angular momentum also follows our right-hand rule convention of torque. Let's look at an example for a mass of 0.15 kilograms on a radius of 0.50 meters with a velocity of 1.1 meters per second. As we said, this would be clockwise motion, so we'll use angular momentum is equal to negative multiplied by mass multiplied by velocity multiplied by radius. We input our values, and our calculator tells us that this would be negative 0.0825, and our units are kilograms meters squared per second. This is slightly different than the units of normal momentum. And if we quickly consider our significant digits, this would be negative 0.083 kilogram meters squared per second. Now, what does the right-hand rule tell us about this negative sign? Well, we point our fingers along the radius vector, curl them towards the velocity vector, and the direction of our thumb tells us that the angular momentum would be into the page, again represented with an X inside a circle, meaning the tail of an arrow. For clockwise motion, we would have an angular momentum that is into the page. Just like our moment of inertia, we need to consider angular momentum when we have infinitely many particles. So what about a spinning disk? In this case, we would still be able to calculate our angular momentum, but we would use the formula that L is equal to the moment of inertia times the angular velocity. Well, this equation is listed as a magnitude equation. Remember, angular momentum is a vector, and we will need to use the right-hand rule to determine the direction. The right-hand rule in this application would be to curl the fingers of your right hand in the direction of the angular velocity, and your thumb will again point in the direction of your angular momentum, either into or out of the page in this case. Let's look at an example. So if we have a spinning disk with an angular velocity of 21 radians per second and a moment of inertia of 1.4 kilograms meters squared, let's calculate the angular momentum. Using our formula, L is equal to I omega, and substituting our values, we can see that we get 29.4 kilograms meters squared per second, which is approximately 29 kilogram meters squared per second. Applying right-hand rule, we would curl our fingers around the disk and our thumb points out of the page. This would correspond to a positive angular momentum. Like its linear counterpart, angular momentum is conserved, but this time in the absence of a net torque. We often observe this phenomena as a changed moment of inertia will correspond to a change in angular velocity. The equations you see will be that your initial angular momentum should equal your final angular momentum. Or we can even break these two variables open and see that our moment of inertia times our angular velocity in the initial phase should be equal to our moment of inertia multiplied by our angular velocity in our final phase. The common example you see is a figure skater. So recall, we can calculate our moment of inertia using mass multiplied by radius squared. Meaning that if we change the amount of mass, which is rare, or its distribution, which is pretty common, it will require a proportional change in the angular velocity as our angular momentum is conserved. So figure skaters take advantage of this by reaching out and pulling in their arms while they're spinning. You may note that hands and arms have low mass relative to the rest of the figure skater's body, but the change of radius is more impactful when it comes to angular momentum. This is because of that squared factor on the radius. So increasing the distribution by 2 meters will be much more impactful than increasing the mass by 2 kilograms. When multiple forces apply to the same lever arm, we can consider the net torque that is applied to that lever arm. The simplified example of this phenomenon is explored using a seesaw. So we would have a thin rod resting on a fulcrum, which becomes the axis of rotation, and then we would have 2 weights, one pulling down on each side, and we would also have a force from the fulcrum that pushes back up. If we're in a situation where there's something called static equilibrium, then we know that there is no net force, which means the beam has no lateral nor vertical acceleration, and no net torque, which means the beam has no angular acceleration. This shows up as multiple equations. This means that the sum of all forces will be 0, or that can be broken down into the sum of all the forces in the lateral direction, or x, is equal to 0, the sum of all forces in the vertical direction, or y, is equal to 0, and the sum of all the torques around the axis of rotation is equal to 0. Now, these are the conditions of static equilibrium. Not every balance problem is in static equilibrium. Let's look at an example. For this example, let's take the seesaw we've already drawn and label on some known distances from the axis of rotation. We'll also know the mass of each block, and let's throw in the total length of the beam and the mass of the beam. The question we're trying to answer is this seesaw in static equilibrium? And if not, find its angular acceleration. Let's move our sketch out of the way. Our strategy here will be to find the total moment of inertia, then calculate the net torque, and using those two values and Newton's second law, calculate the angular acceleration. So the first step, moment of inertia. So the total moment of inertia is the sum of the moment of inertia from mass 1 and the moment of inertia from mass 2 and the moment of inertia from the beam. If we substitute the formulas for a particle at a known distance for each of mass 1 and 2 and the thin rod for the beam and substitute our values, we get a value of 378.927. That's a lot of information. We're going to reuse this, so let's store it in our calculator in memory bank A. Let's calculate the net torque now. So this is the sum of all the torques. Each of mass 2 and mass 1 apply torques. For our convention here, we see that mass 2 will pull down on the left-hand side, causing counterclockwise rotation, so it'll be positive torque. But mass 1 pulls down on the right-hand side, causing clockwise rotation, so it will cause a negative torque. So we'll subtract these two values. Again, substituting for the weight and the known radius, and substituting our values. Keep in mind that we have mass, so we have to include the acceleration due to gravity to make it a force or a weight. We see that we have a net torque of 76.5576 Newton meters. This is positive, so we know that we will be rotating counterclockwise. This means that the smaller mass further away from the axis of rotation is actually causing a greater torque. Let's squeeze the angular acceleration calculation into the side here. So rearranging Newton's second law, we can get the angular acceleration from taking the net torque and dividing it by the moment of inertia. I already have these values in my calculator, so let's substitute the value stored in B, dividing by the value stored in A, and we see that we get 0.2020. Again, more information than we need. This is approximately 0.202. But we have to take a second and look at our units. Our value from B is in Newton meters, and our value from A is in kilogram meters squared. We can substitute for the Newton as kilograms meters per second squared, which gives us kilograms meters squared per second squared on the top, divided by kilograms meters squared on the bottom. So we end up getting an acceleration in per second squared. Remember, this is an angular acceleration, so this means we are getting 0.202 radians per second squared of angular acceleration. Let's look at an actual static equilibrium application problem. The triple beam balances you use in lab will depend on the static equilibrium principle. We're going to consider the scenario below to explore this. We have a witch of unknown mass, but we have a duck with a weight that is known to be 44.5 newtons and a known distance. If we know that this is in static equilibrium, we can find the mass of the witch. Now, one of the things to note is that if this was a balance beam, the duck would have an adjustable radius, and that's how you could bring this into static equilibrium if it wasn't there. Let's clear this picture out and draw our sketch over top of it. So we can draw in a thin rod to act as our balance, and we can draw in the force of tension that holds the thin rod up, and the known weight of our duck, and the unknown weight of our witch. Weight of our duck, we have a force. We can also label in our known radiuses on the balance. Because this is a static equilibrium problem, we know that there is no net force in the vertical direction, and that there will be no torque around the axis of rotation. So we set up. We know that the net torque will be equal to 0, and moving things around, we'll have 0 is equal to the torque due to the duck, which is the weight of the duck, multiplied by the radius of the duck. And again, this is down on the left-hand side, causing counterclockwise rotation, so this would be a positive torque, whereas the witch's torque will be causing clockwise rotation, and it will be negative. We can rearrange and substitute for the weight of the witch, and again do a little bit more algebra to isolate the mass of the witch, substituting our values that we know and calculating for 40.94178 kilograms, which, considering significant digits, would be equal to 40.9 kilograms. In the previous scenario, a single tension was able to hold the two weights of the duck and the witch. This tension was not applied to the physical center of the balance, but at a point that we'll call the center of gravity. Like the center of mass that we've previously seen, the center of gravity can be calculated as an average weight of the entire object. To do this calculation, we take the sum of all the weights multiplied by their distance from one end, and we divide that by the total weight of the system. Note, for objects of constant density and symmetrical shape, the center of gravity is the physical center of the object. So for our two pictured balls and the thin rod between them, individually, the center of mass for each of those objects is at the physical center. We can calculate the center of gravity for this system of masses. So we'll set up our equation and input all the values we know, and then we can calculate to find that the center of gravity of this object is approximately 0.780 meters from the left-hand side. This lets us know if we were able to apply a tension force of 66 newtons at this point, it would be able to balance the entire system. So there would be no net force and there would be no net torque about this point. If we attach this tension at any other point, there would be a net torque on one side or the other. Let's quickly review our new equations of rotational dynamics. We've seen that there's a torque, which can often be calculated as the radius multiplied by the force multiplied by the sine of the angle between the two vectors. We've also seen that Newton's second law can tell us about net torques and their connection to angular acceleration, as the sum of all torque will be equal to the moment of inertia multiplied by the angular acceleration. We've seen that the moment of inertia can be calculated separately from Newton's second law, as the moment of inertia is equal to the mass times the radius squared, and that's for a system of discrete particles. But if we have an infinite number of particles or a rigid shape, we have other formulas which will be available on your formula sheet, but I'm not going to list them here. We also saw two ways to calculate the vector angular momentum, using the tangential velocity and the radius of its circular path, or using the moment of inertia and its angular velocity. And we also saw that the conservation of momentum applies to angular momentum as well. So that our angular momentum in our final stage should be equal to the angular momentum in our initial stage if we have no net torque. And we can break that apart as moment of inertia final multiplied by angular velocity final is equal to moment of inertia initial multiplied by angular velocity initial. Something we didn't have time to talk about today, but is a formula you might find useful, is that we can connect torque and angular momentum. Remember, a net torque will change our angular momentum. So the change in angular momentum will be equal to torque multiplied by the amount of time the torque was applied over. Now for a recap. In this lecture, we continued to explore the consequences of considering circular motion. We explored connections between applied forces and rotational motion, and we saw that applied forces in rotational motion introduces the concept of a torque, which is a force that induces rotational motion. Torques also depend on the moment of inertia for the object, and torque will influence the angular momentum of that object. We also took some time to look at the nature of center of gravity, which is closely linked to the center of mass, and we applied the knowledge we found today to better understand our triple beam balances in our labs. You should now be able to complete the pre-class quiz for this material.